The human mind is a remarkable thing, capable of contemplating the infinite, the infinitesimal, and the abstract. Yet, it is fundamentally shackled by its own biology. We are creatures of three-dimensional space, born into a world of height, width, and depth, and our senses have evolved to interpret reality through this narrow lens. This evolutionary inheritance makes the concept of a fourth spatial dimension one of the most profoundly difficult ideas to grasp. It is not merely a matter of adding another number to a coordinate system. It requires a complete rewiring of our intuitive understanding of space itself. And yet, the human spirit of inquiry has never been content with the limits of its perception. For over a century, mathematicians, philosophers, artists, and scientists have grappled with this challenge, and the result is the fascinating, mind-bending endeavor of visualizing the Tesseract and other four-dimensional shapes. The story of this endeavor begins not with a breakthrough in physics, but with a Victorian mathematician named Charles Howard Hinton. Hinton, a British mathematician living in the late 19th century, was utterly captivated by the idea of the fourth dimension. While the concept of a fourth dimension was not entirely new, it was Hinton who gave it a name and, more importantly, a tangible form that would capture the public imagination. In his 1888 book, A New Era of Thought, he coined the word tesseract to describe the four-dimensional analog of the cube. The word itself is a beautiful construction, derived from the Greek tessera, meaning four, and actes, meaning ray, referring to the four rays or lines that meet at each vertex of the shape. Hinton's contribution was far greater than just a catchy name. He was deeply invested in developing methods to help people actually visualize this impossible object. His approach was one of intense, systematic training. He devised a system using a set of 81 small, color-coded wooden cubes. By memorizing and mentally manipulating the shifting configurations of these cubes, an individual could, Hinton believed, develop a direct feeling of what the block is and, by extension, what a four-dimensional object would be like. It was a form of mental gymnastics designed to break the mind free from its three-dimensional habits. His methods were so elaborate that they required a staggering 81 different colors and an equally bewildering set of Latin names for the various parts of the Tesseract. This training was not just an intellectual exercise for Hinton. It had a profound philosophical and almost spiritual dimension. He believed that gaining an intuitive perception of higher space required one to cast out the self, to rid one's mind of the ingrained concepts of right and left, up and down, that are inherent to our position as observers in a three-dimensional world. He equated this process with the act of sympathizing with another person, implying it was a path to a more profound understanding of existence itself. This work on visualizing the fourth dimension wasn't confined to the abstract world of Hinton's study. In a wonderfully unexpected twist, it led directly to one of the most ubiquitous pieces of playground equipment in the world, the jungle gym. At home, Hinton built a real, climbable multi-cube frame from bound bamboo sticks for his children. His goal was pragmatic: to help his sons master three-dimensional space by physically navigating a grid landscape. He would call out Cartesian coordinates, x2, y4, and direct them to specific positions on the frame. He believed that a solid grasp of the third dimension was the necessary precursor to any conceptual leap to the fourth. Decades later, his son, Sebastian, now a patent attorney, recounted this story at a dinner party. He admitted that he and his brothers never cared much for their father's geometric intent. They simply loved climbing on the structure. This chance remark sparked the interest of a progressive educator named Carlton Washburn, who was seated at the table. Washburn immediately saw the potential of the structure as the ideal piece of school playground equipment. Together with Sebastian and a school headmaster, they sketched out a prototype, built a model from iron pipes, and installed the first permanent jungle gym at the Horace Mann School in Winnetka, Illinois. It was a huge success. The original structure remained in use for over 9 decades, a testament to the enduring appeal of Hinton's invention, which, born from an abstract mathematical pursuit, had become a cornerstone of childhood play. Charles Hinton's legacy is thus a dual one. He gave us both the word tesseract and the jungle gym, bridging the gap between the esoteric realm of higher dimensional geometry and the joyful, physical world of a child's playground. Hinton's work was a catalyst. He inspired a long lineage of thinkers, including the mathematician Alicia Boole Stott, his sister-in-law, who became a gifted geometer in her own right, and scientists, artists, and science fiction writers. His name entered the public consciousness through the writings of pioneers in the field. One of the most famous and influential popularizers of the Tesseract was Carl Sagan. On his seminal television series Cosmos in 1980, Sagan undertook the seemingly impossible task of explaining the fourth dimension to a global audience. His genius was in his use of simple analogies. He began with a creature in Flatland, a two-dimensional world. He asked his audience to imagine how a Flatlander, with no concept of up or down, would perceive a three-dimensional apple passing through its plane. The Flatlander would only see a series of cross-sections, a point that grows into a circle and then shrinks and disappears. The apple itself, the full three-dimensional object, would be incomprehensible. Sagan then used this analogy to explain a tesseract. He explained that just as a three-dimensional cube casts a two-dimensional shadow, a four-dimensional tesseract casts a three-dimensional shadow. He then showed the audience the classic representation of a tesseract, the shadow of the 4D object projected onto our 3D space. He was careful to point out that the image on the screen is not a tesseract. It is just an approximation, a shadow. To demonstrate this further, he used an apple, stamping it onto a surface to show how a 3D object would appear as a series of shapes to a 2D observer. This simple, powerful demonstration of cross-sections made the abstract concept of a fourth spatial dimension accessible and thrilling for a generation of viewers. Sagan's explanation remains one of the most referenced and influential explanations of higher dimensions in popular culture. Beyond these abstract projections, a different, but equally important, method for visualizing 4D objects is through the use of cross-sections. The most common projection involves casting a shadow, but another way to understand the shape is to slice through it with a 3D space. If you were to take a 3D cube and pass a 2D plane through it, the cross-section you would see could be a square, a triangle, or a hexagon, depending on the angle and position of the plane. The same principle applies to a tesseract. If you were to pass a 3D space through a 4D hypercube, the cross-section would be a 3D shape. Depending on the orientation, that cross-section could be a cube, a truncated cube, or even a complex polyhedron like an octahedron. Visualizing these cross-sections is a powerful tool for understanding the structure of the 4D object by breaking it down into a series of familiar 3D shapes. The geometry of the tesseract itself is a beautiful and intricate logical extension of the rules of Euclidean geometry. Just as a cube is created by taking a square and moving it through the third dimension, a tesseract is created by taking a cube and moving it through the fourth dimension. The cube, in its movement, traces out a new shape, ending in another cube. The tesseract is bounded not by faces, but by cubes. This is the reason it is often called a hypercube. It has 8 cubic cells, 24 square faces, 32 edges, and 16 vertices. Each vertex of a tesseract has 4 coordinates, representing its position in 4-dimensional space, and each vertex is connected to 4 edges. To visualize this mathematically, researchers use algorithms to rotate the 4D object in 4D space, just as one would rotate a 3D cube. This 4D rotation produces a constantly changing 3D projection, and by applying matrix math to the 4D coordinates, these projections can be rendered in 3D. When you see a classic, rotating tesseract animation, you are essentially watching the 3D shadow of a 4D object twisting and turning, and the way its internal structure seems to pass through itself is a direct result of this higher dimensional motion. The history of visualizing 4D objects is a story of increasing sophistication and cross-disciplinary collaboration. Descriptive geometry, the mathematical art of representing 3D objects on a 2D surface, provided a crucial language and toolkit. In a 2018 paper, researchers refined a method of double orthogonal projection to create true 3D models of 4D objects. Their technique is analogous to Monge's projection, a classic method in descriptive geometry. The idea is to project a 4D object onto 2 perpendicular 3D spaces. A 4D object is projected onto 2 3D spaces, which are then merged into a single interactive 3D modeling space. This technique allows the user to manipulate the object and study it empirically without relying solely on abstract analytics. It represents a significant step forward in making the study of higher-dimensional geometry accessible to the human mind. This mathematical and scientific work has also inspired a long lineage of artistic expression, becoming a powerful symbol in both high and popular culture. The Tesseract has appeared in everything from avant-garde art to blockbuster films. In the art world, one of the most celebrated depictions is Salvador Dali's 1954 painting, Crucifixion, Corpus Hypercubus, which depicts Jesus Christ being crucified on the unfolded net of a hypercube. In popular culture, the Tesseract is a recurring motif. In Madeleine L'Engle's beloved children's novel, A Wrinkle in Time, the Tesseract is a concept used for space-time travel. In the Marvel Cinematic Universe, the Tesseract is a powerful cosmic object, often shown as a glowing blue cube. In Christopher Nolan's film Interstellar, a Tesseract is a location inside a black hole, used for communicating with the past. These references speak to the power of the concept. It has become a shorthand for the mysterious, the powerful, and the incomprehensible, often associated with space-time manipulation and travel. This ancient fascination with visualizing the impossible has found a vibrant expression in the digital age. Modern 3D modeling software, like Blender, has made creating these visualizations far more accessible. One such project involves using Python scripts within Blender to animate a Tesseract. The code uses functions to apply 4D rotation matrices to the Tesseract's vertices, and then projects the resulting 4D points into 3D space for rendering. This process allows anyone to create a stunning, dynamic visualization of a Tesseract, demonstrating how computer graphics can bring the most abstract ideas to life. Artists have also created physical, kinetic sculptures of Tesseracts. For example, the piece Roundabout 4 Dimensions by Julius von Bismarck and Benjamin Mouse, a kinetic sculpture on permanent display at CERN, makes the concept of a 4D body rotating and casting a 3D shadow a visible reality. The sculpture, in its constant, graceful motion, allows viewers to see the inversion of the 3D shadow as the 4D body turns. The ongoing quest to visualize the fourth dimension is a testament to the power of the human mind to reach beyond its biological limits. We cannot see it, we cannot feel it, and we cannot intuit it. Yet, we have built a rich tradition of understanding it through mathematics, explored its philosophical implications, and even invented toys to help our children grasp the concept of space. From Hinton's wooden cubes and his unlikely gift of the jungle gym to the mathematical precision of descriptive geometry and the breathtaking visual power of modern CGI and kinetic art, the Tesseract is a fascinating case study in human creativity. As the exploration of higher-dimensional spaces continues, as we peer deeper into the quantum world and further out into the cosmos, the Tesseract will surely remain a powerful symbol and a crucial pedagogical tool. It is a reminder that the most important voyages of discovery are often not outward, into space, but inward, into the vast and uncharted territories of the human mind, where the impossible is not an obstacle, but an invitation to imagine.